Well, hello and welcome. We are on activity 17. We are going to be studying, as the title suggests, dilations and similarity transformations. Now, we took some time looking through some other transformations back in Unit 2. So before we go any further, let's just kind of recall those. Remember, we said that they were rigid motions, and think about what a rigid motion is. It's a transformation that does not change the size or shape of a figure. So maybe we're going to see something a little different with similarity transformations. Now, rigid motions are considered congruency transformations mainly because they create congruent figures. That's the idea of a rigid motion not changing the size or shape of a figure in the transformation. So the first one we learned was none other than the translation. We looked at the reflection, and then we looked at the rotation. So these three transformations are referred to as rigid motions or congruency transformations because they create congruent figures. They don't change the size or shape of the figure during the transformation. So keep that in mind today as we start exploring dilations. So before we go any further, let's look at our learning targets. Let's annotate those. So we are going to perform dilations on and off the coordinate plane. We did that with those other transformations, studied them on the coordinate plane, and then removed the coordinate plane from the picture and said, what is going on with these transformations? And then we are going to take some time and describe dilations. So just study them a little bit more in depth instead of just performing them. Actually, describing, studying, analyzing what a dilation does. So we have this really unique idea here about this graphic artist. I believe her name is Kate. That's really tied to what I actually do. I'm actually a freelance graphic designer, so this is a really cool lesson. So take some time, read through this first page, and go ahead and draw a line at the bottom under number 4. And just recall that when we draw a line that just tells us to work through these few items before playing through the video. So read through the text, complete items 1 through 4 before playing through. Okay, so we have Kate here, who's a graphic artist that wants to create 2 different layouts of a brochure for a client to review. So layout A, we're seeing it's a lot bigger, still the same image or the picture, but layout A is clearly a little bit larger than layout B, or the way you could say it is layout B is smaller than layout A. So question 1, what are the coordinates of the vertices of the pre-image? And I went ahead and labeled which points for which. A was at 0, 8, B was at 6, 8, C was at 6, 0, and D was at 0, 0. And I think that's important that you actually label which point is which, because item 3, after you write what the vertices of layout B is, item 3 then asks what's the relationship you notice between the coordinates. Well, anytime we start talking about the relationship between coordinates of a pre-image and an image, we're talking about corresponding coordinates, such that point A in layout A corresponds to point A in layout B. So it's important that we see here from item 1 to item 2 that A 0, 8 goes to A 0, 4. And B 6, 8 goes to B 3, 4. That's going to really help you if you couldn't figure it out. What was the relationship you should have noticed is that the coordinates for layout B are half of the coordinates for layout A. It might be a little hard to tell with those that have 0 in the coordinate. And notice I asked that question here. Why can we not see any change with coordinates that contain a 0? Well, that's because taking half is really multiplying by 0.5. And when we multiply 0 times any number, we still get 0. So it might have been a little hard, especially if you just focused on D. Why is there no change here? Well, because half of 0 is still 0. So it's really important that you label which points are which so you can see which corresponding points and how they change. And then item 4 asks, express the transformation in item 3 as a function. And recall when we did our previous transformations that we can write a function if all of the points essentially obey the same operation. They go through the same, from one input, we use a function, creates a similar output. So I said that each coordinate, so x and y, all of the points, the pre-image points, go to, their image is half of x, half of y, because we're taking literally half of each value. So I added a couple other questions besides the one about a 0. What's happening to the length of each segment, and how does that relate to the answer in item 3? Think about that. So not only is this transformation changing these coordinates, but it's obviously changing the size of our figure. So from A to B was 6 units, and from A to B here in layout B is 3 units. Well, think about how that relates to what we said in item 3. And then just a little bit further thinking here, points A, B, and C appear to be getting closer to what point? And think about why that is. Why are these 3 points, A, B, and C, getting closer, hopefully you figured out, getting closer to point D? And you might be wondering, why did D not move? Why is D still at 0, 0? So let's continue on and see if we can discover why that is. So now if you would, we're going to do something very similar. Go to the bottom of this page under D and go ahead and draw a line under 8D. And just remember, when we draw a line, we're going to work up to that point before playing through the video. So take a look through from items 5 through 8. Okay, hopefully you took a second to work 5 through 8. So here's our third layout, layout C. So obviously a lot larger. And again, go back to what we said on the previous page about how these dilations are affecting not just the coordinates, but the overall size of our figure, the length of the segments. So it says, what are the coordinates of the vertices of the image shown in layout C? Here they are. A is located at 0, 16, B 12, 16, C 12, 0, and D 0, 0. And then it said, what relationship do you notice between the coordinates for layout A, which was our original pre-image, and the coordinates for layout C? So I went ahead and wrote the coordinates for layout A just so you can compare the two here. So A from layout A was at 0, 8. A at layout C is now located at 0, 16. So again, we don't see this obvious change with any coordinates that contain 0, but we see a change from 8 to 16. Now, again, you might be thinking, oh, well, we just add 8 to every number. Well, in order to write it as a function, every single coordinate has to obey that same rule. So if you said add 8 here, well, 0 plus 8 is not 0, that's 8. So obviously, the addition of 8 is not the correct function. And you can verify that with B as well. We see that 6, B is located at 6, 8. Now B is located at 12, 16. So maybe we could say that we add 6 to our x value each time, right? Well, we add 6. Well, then we go back to A and say, well, 0 plus 6 is not 0. It's so again, when we write a function, you have to ask yourself, is everything obeying the rule? Is every value obeying the rule? So the coordinates for layout C are twice the coordinates for layout A. And that's all of the values. All of the values in the coordinates are twice that for layout A. So if that's true, if all of the coordinates obey that rule, then we can write them as a function. And the way we write in algebra that something is twice as large is we say 2x or 2y. In this case, we're using 2x and 2y because we're talking about coordinates changing. So here's our function, xy, which is every point goes to. The x gets doubled, the y gets doubled. That's simply what we're looking at there. And what you're discovering, these two transformations that you're performing, is called a dilation. It's a transformation that changes the size of a figure. Think about what I was asking earlier, what happened to the size, but not its shape, right? These brochures are still rectangles. And not just rectangles, but similar rectangles. There are, in fact, rectangles that can be actually different in shape. So a dilation is a transformation that changes the size of a figure, but not its shape, by something called a scale factor. We use this idea of factor in algebra to refer to multiplication and how every number has factors that can multiply to create that number. And we saw this term scale implying that something can get larger or smaller, right? So the scale factor determines whether the transformation is a reduction. When we reduce, we make it smaller, or an enlargement, we make it bigger. So we've been looking at a dilation that changed the size of the figures, but not their shape, using something called a scale factor. So A to A says, what is the scale factor for the transformation of layout A to layout B? I wrote the function over here that we wrote for it. XY goes to 1/2 X, 1/2 Y, and notice what I said the scale factor was. K is 1/2. So really, when we write the function, that value that you put in front of your image coordinates, that multiplying value is your scale factor. It's K. So ask yourself, if layout B, was it a reduction or enlargement? Maybe you need to go back and see that layout B is actually a reduction. It's smaller than layout A. It should be obvious, even if you don't look at the coordinates, just look at the length of each segment to determine if it's a reduction or an enlargement. Now let's look at item C. What is the scale factor for the transformation of layout A to layout C? Again, I wrote the function over here that says xy goes to 2 times x, 2 times y, and there again in the function is our scale factor. So K is 2 in this regard. And remember when we turned the page, we saw how much larger layout C was from layout A. So we refer to this as an enlargement. Now, obviously, these aren't the only two scale factors that we will ever use, 1/2 or 2. So as we transition to item 9, think about what's happening to these images depending on what the scale factor is. Before we go there, I have this other question. We mentioned on the previous page, why should we believe point D is not changing locations besides that it's located at 0, 0? Think about it. All of these points, A, B, and C, in this case, are getting further from point D in relation to where they were on layout A. So why is that? Well, think about what happened with a rotation. Points in a rotation never got closer or further away from the center of rotation. So what we're actually exploring here with point D is actually the center of dilation. But because the dilation does change the size and shape of a figure, points are getting closer or further away from the center, depending on, boom, boom, pow, the scale factor. So keep that in mind as we go forward. So D, not just because it's 0, 0, and we multiply 0 times anything, we still get 0. D, located at the origin, is our center of dilation. And everything is going to get closer or further away from it, again, depending on if we are reducing or enlarging it. So let's press on. Now, if you would, go ahead and draw a line under item 10. So pause the video, read through 9 and 10, go back and look. I believe item 8 should really help you with 9 and 10. So pause the video, try these on your own before playing through. So think through this for a second. Number 9, in general, for what values of K, scale factor K is a dilation or reduction? We saw that with a scale factor of 1/2 that it was a reduction. So think about why that is. Well, in general, if K is less than 1, like 1/2, it's a reduction. But think about what could happen if K was 0. Well, if you like we said, if you multiply anything times 0, it's 0. So in other words, if we multiplied it by 0, it would positively disappear, right? Multiplying by 0 becomes nothing. So I wrote this note over here. Why do we have to clarify the scale factor for reduction has to be greater than 0? So we're actually going to add this part for this rule here that if K is less than 1, we should also say that K has to be greater than 0. So in order for a dilation to be a reduction, K has to be less than 1, but greater than 0. You might be thinking, well, why can't it be negative? Well, you're right. Think about what a negative number would do on the coordinate plane. You're right, negative numbers in our bank account is bad, but negative numbers on the coordinate plane actually do something rather interesting. So we have defined that for a reduction, the scale factor has to be less than 1, greater than 0. Not just any fraction, right? A lot of students want to say, oh, fractions. Well, I could say that 3/2 is a fraction. But 3/2 is the same as 1.5, which 1.5 would actually create an enlargement. So we can't just say, oh, all fractions are all decimals, right? Because there are improper fractions that are actually greater than 1. So keep that in mind here when we write these general rules. What really type of values create a reduction? And that's any values less than 1 but greater than 0. So item 10, for what values of scale factor k is a dilation and enlargement? Well, anything greater than 1. Because 1.1, 1.2, 1.5, 3/2 like we wrote here. Any value greater than 1 is going to make it larger. So then I wanted to add this question to the mix. What do you believe happens to a figure if k equals 1? Well, what happens to our values when we multiply anything times 1? Well, they don't change, right? So that's why we're defining not anything equal to 1 here, but for a reduction less than 1, and for an enlargement greater than 1, because if we were to use scale factor 1, we would see no change. So keep that in mind why we're being very specific about the rules that we're writing on item 9 and 10. Now, if you would, go ahead and draw a line below 12. Complete items 11 and 12 before playing through. Okay, so if you couldn't pick up on it, 9 and 10 and 11 really are trying to get you into a more general idea of what's happening when we perform dilation. So 11 said express regularity and repeated reasoning. A pre-image point, P, we often use P for any point, has coordinates located at A and B. How can you find the coordinates of the image? Remember, image is after the transformation, in this case, after a dilation. How can you find the coordinates with any given scale factor? Well, the operation here that we're seeing is we use multiplication. Now, some of you might be thinking, oh, well, fraction 1/2, you're really dividing by 2. Sure, but dividing by 2 is still the same thing as multiplying by 1/2. So in general, we say with a scale factor, we're multiplying each coordinate by that scale factor k. And so in general, when we write a function for a dilation, we're going to see that every point goes to k times x, k times y. And so that value in front of x and that value in front of y are our scale factor k. Now 12, I like 12, they kind of do a little review here of one of our other transformations, the translation. It says, recall the composition of transformations as a series of 2 or more transformations back to back. So we have this rectangle located at A06, B46, C40, and D00, and we create rectangle A prime, B prime, C prime, D prime using several transformations known as a composition. So our first transformation is a translation using this function, and then it says followed by a dilation with scale factor 1/2. So here is that work over here. So here are all our pre-image points. So if we use the first translation function, x minus 4, y minus 6, we get these coordinates. That's where A, B, C, and D go after the translation. And then we have to do one more transformation using that scale factor 1/2. So A prime is now located at -2, 0. B prime is located at 0, 0. C prime is located at 0, -3. And D prime is located at -2, -3. So after a translation, then a dilation, that's where those points would end up. And so think, is this a reduction? Did the translation in our transformation throw us off? No, it's still a reduction. It's in a new location, definitely because of the translation, but it's still a reduction nonetheless because we use a scale factor less than 1. Now, before we go any further, I really want to pose this question. You can look at this, check your understanding. It's a really strong one, great practice. But I want to ask, is there another way to determine the scale factor? Maybe you had some issues here or on the previous problems identifying the scale factor between a pre-image and an image. So is there another way to determine the scale factor? Well, as I mentioned, we can actually look at the lengths of segments to determine how the dilation affected the image. So one of the best ways to determine the scale factor if you're having an issue, especially looking at the coordinates, is you take the you take the length of your image. So we'll say K equals the length of maybe one segment of your image, and you divide it by the pre-image. And I'll use an example from our previous problems. Let me scale back here. So the distance from A to B on layout C was 12 units wide, right? So 12 units. And then we go back to layout A and say, well, what's the length from A to B? Well, from A to B is 6 units. So let's use that idea here and say, what is K if we have A prime, B prime from layout C compared to the length from layout A? Well, A prime, B prime in layout C was 12 units. AB from layout A was 6 units, and 12 divided by 6 is 2, our scale factor 2. So here's another way, if coordinates are throwing us off, we can actually look at the length of the segments to determine the scale factor. And it's always image divided by pre-image. Think about what would happen if we swap these two. Well, sure, we could compare them a little bit differently. We could look at the pre-image compared to the image by swapping AB and A prime, B prime. But to determine the scale factor, it's the new divided by the old. And if we had swapped it, it would be 6 over 12, or 1/2, which is clearly not what's happening in layout C, because layout C was an enlargement. So here's just another way to help determine the scale factor as we press on through dilations. So notice the math term over here. We mentioned it a second ago. The center of dilation is a fixed point about which all points are enlarged or reduced. Whatever the center of dilation is, and for the most part it's the origin, those points are going to get closer or further away depending on if it's an enlargement or a reduction. So think about it. If it's a reduction, are points going to get closer to the center of dilation, or are they going to get further? And if it's a enlargement, are points going to get closer or further? So this page, items 15 through 19, really explore what happens when the center of dilation is not the origin. Now, we're not going to look at that together, but it's excellent practice here. There's some lingo here that you are certainly welcome to look at, and really heightens your understanding of dilations, especially when the center of dilation is not the origin. We're not going to look at that together. We're actually going to go and jump on to item 20. So we've taken some time and looked at dilations on the coordinate plane. Now we're going to use geometry software to explore dilations off the coordinate plane. Now to do that, we're going to use our trusty GeoGebra. So I'm going to write that here for those that want to use this resource. We use this quite a bit to kind of explore dilation so we don't get hung up on the drawing of it. We can use the software to help us actually do the drawing for us. So before I hop over to GeoGebra, let's just take a quick look at what we need to be thinking about. So first, we're going to perform a dilation. We're going to plot a point for the center of dilation. We're going to draw a triangle ABC and dilate it using a scale factor of 2. Notice they're not saying that the center of dilation has to be on the original pre-image. It could be inside the original pre-image, and so we're going to do a little exploring there. But they've told us that the scale factor is 2. So right off the bat, think about it. Is it going to be an enlargement or a reduction? So that's going to help us with item B. This says compare and contrast the pre-image and the image. So maybe we're going to see how a scale factor of 2 creates a new image, and we're going to have to compare and contrast those. Then item 21 says perform dilations on triangle ABC using different scale factors. We're going to explore when the scale factor is greater than 1, like the example 2, where K is 1, and where K is less than 1 but greater than 0. So that's what we're going to be performing a couple transformations. So we'll actually be doing these together. So I'm going to hop over to GeoGebra, and we'll start with item 20. So they have asked us to draw triangle ABC. So they didn't specify how large triangle ABC is. So remember, to draw a polygon, just click on polygon and then select 3 points. And to close the polygon, just click on point A again. So here we have some triangle ABC, and they also asked us to plot a point that would be the center of dilation. So the first thing I want to do is explore when the center of dilation is not necessarily on the original figure or not even within it, but just outside the original figure. And so they are asking us to perform a dilation with scale factor 2. So I'm going to click on More, go to the Transform section, and then dilate from a point. So we are going to select our object, select our center of dilation, and then it asks for the factor, the scale factor, and they told us to do 2. So I'm going to go and select that. Now notice that my image obviously got a lot larger, so I'm just going to zoom out so we can see it. So here we have A prime, B prime, C prime, the image of ABC after a dilation of scale factor 2. So I think we performed that pretty well. Notice, as we mentioned with on the coordinate plane, how much further A prime is from point D. Because it's an enlargement, these image points are going to get further away from D. So item 20B says compare and contrast the pre-image and the image. So we're going to perform a couple things using GeoGebra to help us see that. We're going to start with some measurements. So we know the scale factor is 2. So let's go to distance. Let's talk about how scale factor, obviously we're not dealing with any coordinates. How does it affect distance? So let's see what the distance from A to B was. So on my GeoGebra, the distance from A to B was 4.1. So we know the scale factor not only affects coordinates, but it should affect the length of the segment. So ask yourself, if the length from A to B is 4.1 and the scale factor was 2, what should be the length from A prime to B prime? Well, hopefully double that, right? So let's see. And there we have it. 4.1 times 2 is 8.2. Now, since we have set the scale factor as 2, all of these other segments should obey that same rule. But what I really want to explore is what we said a moment ago. What happens to the distance between corresponding points? So let's first find the distance between one of our points and the center of dilation. So the distance from A to D is 4 units. Just happens to be a nice even number. So think about what happens to the distance from A prime to D. So if the scale factor is 2, and we know that is changing the length of all of these segments, what's happening to the distance from A to D, from A prime to D? So let's explore that. From A prime to D, can you guess what it should be? Well, 7.9 or 8. So what we're seeing here is not only is the scale factor affecting the size of our shape, but it's also affecting the distance by that same scale factor. We can explore that a little bit further here. Let's look at point B to the center of dilation. We have 5.4, that distance there. So the distance from B prime to the center of dilation, D, should be double that. And there it is 10.8. So not only is the scale factor affecting the size of our figure, but it's also altering the distance by that same scale factor. Now, what I want to do now is explore the angle. So I'm going to back out a little bit and just kind of see. We know that obviously the shape or the size is 2 times bigger, but they led us to believe that a dilation does not change the shape of our figure. And clearly these are 2 triangles, but are they similar triangles? The easiest way to determine if they are similar triangles is look at the angle measures. So I'm going to go measure an angle. Start by measuring angle A using points C, A, B. And I see that it's 44.2. Well, what do you suppose the measure of angle A prime should be? If these 2 triangles really are the same shape, what should the measure of a corresponding angle be? We know that the length of the sides definitely change, but what's the measure of the corresponding angles? So let's look now at the measure of A prime, angle A prime. And look, it's the same degree measure. So when we imply that we're not changing the shape, we're really not altering the angles. That's why when we studied our triangle congruence, angle, angle, angle was not a congruence criteria, because we can have two triangles, in this case, that have the same angle measures, but clearly not congruent, right? So the size from A prime to B prime is twice the length from A to B, but the measure of angle A is the same as the measure of angle A prime. So we've explored a dilation when the center of dilation is obviously not within the parameters of the actual figure or even on the figure. So what I'm going to do now is I'm going to take this center of dilation and move it. Click on this. So watch what happens as I move point D closer to the pre-image. Look what happens to the image. Obviously it gets closer to it. Now, in fact, when I put the center of dilation within the pre-image, the image is perfectly surrounding it. So what we're seeing here is how this relationship works in relation to the center of dilation. Watch what happens when I put the center of dilation on one of the points of the pre-image. If I would line up point D and point C, well, C prime is in the same location. Think about it. So however far a point is from the center of dilation, that's how the relationship's going to be depending on the scale factor. So if the center of dilation is on the shape, then that point's not going to move. Just how we saw that the center of dilation, when it was the origin, it did not move either. Points got further or closer to it. The last thing I really want to point out as we move point D around is how moving or altering the center of dilation is not affecting the length of our segments, and it's not affecting the measure of our angles. But there's one measurement that I want to again point out. Let's get back to measuring the distance from a pre-image point to the center and from an image point to the center. We said that there was something interesting here. Not only are the lengths of segments being doubled, but obviously the distance from corresponding points to the center of dilation are being doubled. And I want to see if that remains true when we start moving that center of dilation. So the distance from A to D is 4.1. So from a pre-image to the center, and from an image to the center is now 8.2. Let's see what happens. Does that relationship stay as we move the center of dilation? So let's move it within it. Look here. So the distance from A to D, which is behind this little mark here, the distance from A to D is 3.1. The distance from A prime to D is 6.2, double that. So regardless of where the center of dilation is, whatever the scale factor is, that's going to determine the distance of the image from the center of dilation. So not only is it affecting length, but it's also affecting distance here. So keep that in mind as we explore these dilations. So we did quite a bit of comparing and contrasting the pre-image and the image, so I'll add a little answer here. So I took a moment and said the image is an enlargement of the pre-image, so there's that contrasting. They're obviously different sizes. In fact, the length and distances of the image are doubled, but, and here's the comparison, corresponding angles are congruent. These shapes are actually very similar. They don't have the same size, but they do have the same shape. So now item 21 wants us to explore, we kind of messed around where the center of dilation was, but they want us to explore using different scale factors where k is greater than 1, and we kind of saw that already, what happens to it, where k is 1, and where k is less than 1 but greater than 0. So before we jump to GeoGebra, we want to know how, in general, a dilation transforms a figure based on those scale factors. Do dilations preserve angle measures? And we kind of already hinted that a little bit, and we need to justify our answer. And then, is a dilation a rigid transformation or not? So let's jump over to GeoGebra and start playing around with what happens when our scale factors are not just greater than 1. So I'm going to back this up all the way to our original pre-image triangle ABC and our center of dilation D. And we'll go and keep that center of dilation outside of our pre-image. So we want to perform a dilation when the scale factor is 1 and see what happens here. You might already be guessing what's going to happen. So we select our object, select our point, and let's perform a dilation with scale factor 1. Well, as you probably guessed, we talked about it a little bit. When the scale factor is 1, there's no change because multiplying by 1, we get that same number, right? 2 times 1 is 2. 3 times 1 is 3. 4 times 1 is 4. And so when we use a dilation with a scale factor of 1, we're going to see no change. In fact, even if I were to move the center of dilation, notice there's no change. So a scale factor 1 is not going to change the length of our segments or alter the distance between the points in the center with corresponding points. So now let's back that out and let's see what happens when our center of dilation is less than 1. So think about it. In enlargement, we obviously saw that the points got further away from the center of dilation. Let's see what happens with the reduction. So click on our pre-image, our center of dilation, and let's do something besides 1/2. Let's do 3/4 or 0.75. Well, look, our points actually got closer to the center of dilation, but how much closer, right? So we could compare those lengths. We know that obviously less than 1, we're going to alter the length of our segments. Clearly, they're a different measure. So let's do that. Let's do some exploring here now that the dilation is less than 1. Let's start by looking at our distances. So the distance from our pre-image A to pre-image B is 4.1. So we should see something that's 3/4 of 4.1 roughly. And the distance from A prime to B prime is 3.1. And I believe 4.1 times 3/4 or 3/4 of 4.1 is roughly 3.1. So we're seeing that that's affecting the distances between corresponding segments. We're also seeing that distance between corresponding points in the center of dilation. So let's look at the distance from A to D, which is 3.5. So we should be seeing roughly 3/4 of 3.5. So let's look at from A prime to D, which is 2.6. And that is 3/4 of 3.5. So again, not only are we affecting the length of the segments, but we're affecting the distance to the center of dilation. Now let me back that out, clean it up, and let's just once again explore what's happening to these angles, because I believe item B asks, are the angles preserved? We saw with an enlargement, the angles don't get bigger. So with a reduction, do the angles get smaller? So let's explore that. Let's look at angle A of our pre-image, which is 44.2. Obviously, it was still 44.2 from our previous dilation. Now let's look at angle A prime. It should be 44.2. So yes, what we're seeing here is not only does an enlargement not change the angles, but a reduction doesn't change the angles as well. They're affecting the lengths of our segments and the distances to the center of dilation, but they're not altering the shape. They're not changing the measures of our angles. So let's go back to item 21 and answer items A through C. So hopefully you took a moment to answer item 21. A says, describe how in general dilation transforms a figure. We saw even when we moved the center of dilation, we moved or changed the scale factor, we're seeing that it changes the size but not the shape. So what really determines the shape of these figures, in this case the triangle? Well, that's what item B refers to. Do dilations preserve angle measures? Justify your answer. And we saw that with the drawing. Yes, the lengths of segments increased if enlargement or decreased if reduction, but the angles did not change. So what is really determining the shape of our figure and how they have the same shape is what's really going on with these angles. Item C, is a dilation a rigid transformation? They kind of recalled what the definition of a rigid transformation, rigid motion is where the size and shape are preserved. Well, is a dilation a rigid transformation? Absolutely not. A dilation does not preserve size. It does preserve shape, but it doesn't preserve size. So we can't define it as a rigid transformation or rigid motion. Now, the last part of lesson 17.1, we want to go back and look at the notation we might see when the dilations are not on the coordinate plane. So dilations don't have to be performed on the coordinate plane or with the use of software. Here's a more general definition of a dilation. So take a moment, read through this text, go back if you need to, and refer to our previous understanding of this notation when off the coordinate plane before playing through the video. So given a point O, which will be our center, so for the most part it's been point D, but point O, which is usually the origin, and a positive real number K, which represents the scale factor, the dilation with center of point O and scale factor K maps point P. Remember, it's just a general idea. P is our pre-image point to P prime, which is our image, where P prime is the point on ray OP, such that the distance from O to P prime. Remember, we talked about how it's not just affecting the coordinates, it's affecting the distance. The distance from O to P prime is the distance from O to P times the scale factor. That's really what's going on here. The scale factor is not just changing coordinates, it's changing lengths. So a dilation centered at point O with scale factor K can be written in this function notation, where O is our center of dilation, K is our scale factor, P is our pre-image, and P prime is the image. So here we have this example. The figure shows a dilation with a scale factor of 3 because, and I like that, because, not because we made it be that, they're comparing the lengths. They're saying that the distance from O to P is 3 times the length from O to P prime is 3 times the length from O to P. So if we call the distance from O to P x, the distance from O to P prime would be 3x. That's what we were observing on GeoGebra. Not only is it changing the lengths of these actual segments on the figure, it's changing the distances from these corresponding points. In fact, I'll actually draw a line here through points D, A prime, and A. So think about it, this was a reduction of 3/4. So these points, the center, the pre-image, and the image are all on the same line. That's what it's referring to. That's why they use the ray. And in this case, A prime is getting closer to point D on that line because it was a reduction. Now look at this example. P prime is getting further away from point O because it's an enlargement, it's scale factor of 3. So whatever the distance from O to P was, we call it x here, the distance from O to P prime is 3 times that. So how would you write the dilation above in function notation? So we know that the center of dilation has to be O in this case. Why? Because P prime is getting further away from point O. So dilation, the D, obviously I didn't say that over here, but the D stands for dilation. Using center O, scale factor 3, we're going to take our pre-image point, dilate it using scale factor 3, center O, and we're going to get, as a result, our image of P prime. Now, we don't typically do this together, but I think the check your understanding would take it a little step further to help us with the understanding of lesson 17.1. So if you would draw a line under the check your understanding or do the workout to the side, pause the video, and try to work through 23 and 24 before playing through. Okay, so there's 2 truths right here in item 23 that you might not recall from previous geometry classes, but triangle XYZ is an isosceles triangle with a base angle of 65 degrees. So let's just talk about some truths of what an isosceles triangle is. And there's obviously a reason they're telling us that. So an isosceles triangle, by its definition, is a triangle with 2 congruent sides. So for this example, we have these 2 sides that are congruent. Well, as we studied how sides and angles often relate to each other in an isosceles triangle, if two sides are congruent, two angles are congruent. And those two angles are the angles that are opposite of the congruent sides. And these two angles that are congruent in an isosceles triangle are called base angles. So they're actually telling us a lot here because base angles are the two angles that are congruent in an isosceles triangle. So if we know one base angle is 65 degrees, we actually know two of the angles are 65 degrees. And it says the triangle is dilated by a scale factor of 2/3. What are the measures of the angles of triangle x prime, y prime, z prime? Well, we know a dilation does not affect the measure of angles. So the tendency here is to take 65, 2/3 of that. I see that all the time. Remember, a dilation does not change the shape of the figure. It does not affect the angles. It only affects the sides or the segments. So we're going to have the same measures of angles from our pre-image to our image. So let's figure those out. As I stated before, if one base angle is 65 degrees, these two angles, because two base angles are congruent, they both have to be 65 degrees. Well, you might be asking yourself, how do you find the third then? Well, one truth you might not remember is that the three angles of any triangle, including isosceles, equilateral, scalene, any triangle, the three measures or the three angles have to sum to equal 180 degrees. So if you know two of them, in this case are 65, you should be able to find the third. Well, 65 plus 65 is 130. How many more degrees do I need to make 180? Well, that's 50. So the three measures of the isosceles triangle, even dilated by a scale factor of 2/3, are 65, 65, and 50, the same as triangle XYZ. I think that's really important to emphasize here. Now, 24, they just wanted you to work on a little notation, function notation, when we're off the coordinate plane. So dilation is centered at point 0. So there's the center of dilation. Scale factor 1/4, such that, and I love that they're continually emphasizing this, not only is the scale factor, changing distances, but what distances are they really changing? The distance from O to P prime is 1/4 the distance from O to P. And it says write the dilation function notation. So D for dilation, 0.0 for our center, 1/4 for the scale factor. So if we take any point P dilated using O and the scale factor 1/4, we get the resulting P prime image. So that is lesson 17.1. Be sure, as always, work on the lesson 17.1 practice and go back and reevaluate your learning targets to see if your understanding of those learning targets improved at the end of this lesson. Thank you for watching.